The title of her talk is On a Type of Lightlike Submanifold of Poly-Norden Semi-Riemannian Manifold. Please, you are welcome to do your presentation, Professor Selcen.
Thank you. Can you hear me?
Yes, we can hear you.
Okay. I think my screen is also shared.
Yes, everything is okay. If you are ready, you can start.
Yes. Thank you. First of all, I would like to thank organizers for such a nice webinar. In this talk, I will present one of our studies on lightlike submanifolds of Poly-Norden Semi-Riemannian manifolds. It is well known that the submanifold theory in semi-Riemannian manifold is more complicated than the Riemannian case. Because the index symmetric on a lightlike submanifold of semi-Riemannian manifold is a degenerate one. So there exists an non-trivial intersection of tangent bundle and the normal bundle. Dougal and Bijancu initiated the study of lightlike geometry of submanifolds in semi-Riemannian manifolds by introducing a non-degenerate screen distribution to construct a lightlike geometry. Their approach is known as an extrinsic approach. For another approach, I can refer the Kupelis paper and books. Dougal and Bijancu defined CR lightlike submanifolds of indefinite Caroline manifolds as a generalization of lightlike real hypersurfaces. But it is known that CR lightlike submanifolds do not contain invariant and totally real lightlike submanifolds. So Dougal and Shahin introduced screen CR lightlike submanifolds, which include invariant submanifolds as well as the screen real submanifolds. After this definition, a generalization of CR lightlike submanifolds and screen CR lightlike submanifolds, and it's called generalized CR lightlike submanifold, was given by again Dougal and Shahin. But again, it is observed that the real lightlike curves are not included in these types. So screen transversal lightlike submanifolds of Caroline manifolds, which contain real lightlike curves, were introduced in Dougal's and Shahin book again. In the reference 21, the authors defined a new type of lightlike submanifolds, and this type is called screen transversal CR lightlike submanifolds, and it contains CR lightlike submanifolds and screen transversal lightlike submanifolds as particular cases. Let me remind some basic notations about metallic means and bronze mean. For any positive integer p and q, the positive solutions of the equation given by 1 are called as metallic means, and they are also known pq metallic numbers, and they are denoted by sigma pq and given by equation 2. By using these metallic means, metallic Riemannian manifolds and their submanifolds were defined by Redcanu, Kresmeriano, and Blaga. And also different types of submanifolds in golden and metallic geometry have been published in literature. In a different meaning, a new bronze mean introduced by Kalia. It is known that metallic means family include bronze mean, silver mean, golden mean, and etc. But the bronze mean given by Kalia cannot be expressed with sigma pq for any positive integers. So it is a different ratio, and one cannot reach this mean by using metallic means family. Inspired by the definition of Kalia, Professor Shine introduced a MIP-type manifold called almost Poly-Norden manifolds, and we study non-degenerate submanifolds of such MIP-type manifolds, and it was published in Turkish Journal of Mathematics. And in this article, we studied discrete transversal Cauchy-Riemannian lightlike submanifolds of Poly-Norden Semi-Riemannian manifolds. We present an example, and we examine some integrability conditions of this type submanifolds. The positive solutions of equation 3 is called bronze mean. This is the definition of Kalia, and this bronze mean is given by equation form and denoted by df. Using this bronze mean, Shine defined a new manifold AQ with such a bronze mean. Let us give the definition of almost Poly-Norden Semi-Riemannian manifold. Let M tilde be a differentiable manifold endowed with a 1-1 type tensor field satisfying equation phi. Then phi is called an almost Poly-Norden structure, and M tilde is called an almost Poly-Norden manifold. If we can give an example here, in 4-dimensional real space, let us define phi, 1-1 tensor field, phi like this, then it is easy to see that this tensor field satisfies the equation phi. So 4-dimensional real space is an almost Poly-Norden manifold with the structure phi. If a semi-Riemannian matrix G tilde satisfies equation 6, then G tilde is called phi compatible. And in this case, this triple is called an almost Poly-Norden semi-Riemannian manifold. And phi is symmetric with respect to G tilde, we can see it here. And we will suppose M is different from 0 because when M is 0, in this case, we obtain the well-known Norden manifold. So we choose M is different from 0. And almost Poly-Norden Semi-Riemannian manifold is called just Poly-Norden Semi-Riemannian manifold if the structure phi is parallel with respect to the TÜBİTAK connection on M tilde. And now we recall some basic notations for lightlike submanifolds. Let M tilde be an M plus n dimensional semi-Riemannian manifold and M be an n-dimensional submanifold if the induced metric on M is degenerate and the rank rad Tm is equal to R, then M is called a lightlike submanifold. Rad Tm is the radical distribution, and it is defined by the intersection of tangent bundle and the normal bundle of the submanifold. Since tangent bundle and the normal bundle are non-degenerate vector subbundles, there exists a non-degenerate distribution STM and STM curve of rad Tm in tangent bundle and the normal bundle. And these vector subbundles are called by screen distribution and screen transversal bundle of submanifolds. And by this definition, we can write 10 and 11 for tangent bundle and normal bundle. And in view of an orthogonal complementary subbundle of STM curve to STM in the ambient in the tangent bundle of the ambient manifold, we can write this decomposition given by 12. And this is an important and basic theorem for lightlike submanifolds. By using this theorem, we can say that there exists a complementary vector bundle LTR-TM, which is called a lightlike transversal bundle of rad Tm, and the basis of this bundle satisfying 13. But again, by this theorem, there exists a complementary but not orthogonal vector bundle, TRTM to TM in the tangent bundle of the ambient manifold, and this vector bundle is called transversal vector bundle, and the following two decomposition are whole. Finally, by using the previous decompositions, we can write the tangent bundle of the ambient manifold like this. And we have two parts here for the ambient manifold, TM and transversal bundle. For submanifold, for light-like submanifolds, and in general submanifold theory, Gauss and Weingarten equations are the important equations investigating the submanifold geometry. And the Gauss and Weingarten equations of the submanifold M is given by 17 and 18. By using the projections from transversal bundle to light-like transversal bundle and transversal bundle to cosecrene bundle, we can write Gauss-Weingarten formulas like these equations. Also, there are some relations between the second fundamental forms and the shape operator, and these relations are given here. And it's important to note that the induced connection on light-like submanifold in general is not a metric connection, and it satisfies equation 29. But it is important again to say that the induced connection on the screen distribution is always a metric connection. Again, the relations between the shape operators and the second fundamental forms of the vector subbundle. And let us give the definition of screen transversal TR light-like submanifold. For a light-like submanifold of a Poly-Norden Semi-Riemannian manifold, if the submanifold satisfies the following two conditions, then it will be called a screen transversal TR light-like submanifold. The first condition states that there exist two subbundles of the radical distribution such that the equation 33 is satisfied. The second condition is that there exist two again subbundles of the screen distribution such that the equation 34 is satisfied. From the definition, we can write the tangent bundle of the submanifold as in equation 35, and here D and D hat is given like this. Also, for such a submanifold, we have these characterizations. Let me give an example. We are now in our 12 with index 4, and our semi-Euclidean metric has signature like this. And we take phi, we define phi like in this equation. And it is easy to see that phi is a Poly-Norden structure on M tilde. Then we define a submanifold like this equation 39. And this is a 7-dimensional submanifold, and its tangent bundle spanned by these 7 vector fields, and these vector fields are given by 40 and 41. Here, M is a light-like submanifold, and its radical distribution and screen distribution are given like this, and first one is spanned by psi1, psi3, and screen distribution spanned by these 5 sections. We can see that the psi1 image of psi1 under phi is equal to psi2, and it belongs to the screen distribution. So we can choose d alpha and d beta like this. And also we see that psi 5, image of psi 5 under phi is equal to psi 6, and it is again in screen distribution. So we have the ring spanned by psi 5 and psi 6, and light-like transversal bundle is spanned by N1 and 2. Also, for other parts of the submanifolds and the complementary distributions and vector subbundles, we have these equations. So L tilde, L ring, and S Tm perp, S tilde, and D prime can be given in these equations. So M is a screen transversal CR light-like submanifolds of M tilde. By using the projection morphisms, and there are many distributions, so we need many projections. By using these projections, we investigate integrability conditions. So if we denote the projections from Tm to these distributions like that, then we write equation 45 for a section in tangent bundle, and by you.
Your last word, please. Your last word, please.
Okay. And phi u can be written in 46. Again, applying phi, we can write phi u like this. Similarly, if we denote the projections for the sections in TRTM, transversal bundle of M, we can write phi v like this. We choose the manifold Poly-Norden one. So by using these relations, we give our main result. The first one is the integrability of the distribution of D. The distribution D is integrable if and only if these two conditions are satisfied. I will skip proof. And again, distribution D hat is integrable if and only if the equation 53 is satisfied. The proofs are based on the integrability definition of the distributions. If D defines a totally geodesic population and the necessary and sufficient conditions for that is phi h u v has no component in the tangent bundle, and necessary and sufficient conditions for D hat defines a totally geodesic population is this one. And for D geodesic screen transversal CR light-like submanifolds, we can give the last result. The distribution D defines a totally geodesic population on M tilde if and only if M is a D geodesic one. And these are the references we use. Thank you for listening.
Thank you so much for your talk, Professor Perktas. And now we will continue with my colleague, Selcen Yuksel, for the closing talk. Have a nice evening. See you soon.